Everyone. Hello, everyone. Good afternoon and good evening. Thank you for joining us today for this plenary that will be given by Professor Vidya Madhavan from University of Illinois at Urbana-Champaign. Professor Vidya, thank you for accepting our invitation, and let me introduce you first. So condensed matter physicist Professor Vidya investigates fundamental problems in quantum materials, where interactions between spins, charge, and structural degrees of freedom lead to emergent phenomena. She uses the tools of scanning tunneling microscopy, STM, scanning tunneling spectroscopy, spin polarized STM, and molecular beam epitaxy to unravel the mysteries of complex systems at the atomic scale. Her group carries out challenging, high-risk experiments wherein the possibility of discovering new phenomena is very high. Her team's recent work has focused on STM studies on complex oxides and thin films and topological materials. Professor Vidya received her bachelor degree in metallurgical engineering in 1991 from Indian Institute of Technology at Chennai, and master technology degree in solid state materials in 1993 from Indian Institute of Technology at New Delhi. She held a postdoctoral appointment at the University of California in Berkeley, and before joining the physics faculty at Boston College. She received an NSF Career Award in 2007, and Professor Vidya joined the faculty of the University of Illinois at Urbana-Champaign in 2013. Professor Vidya was also nominated a fellow by the APS Division of Condensed Matter Physics, and the citation says, for major contributions to the study of topological phase of electronic matter using advanced spectroscopy imaging STM. So today, Professor Vidya will talk about creating and measuring the elusive Majorana Fermion. So Professor Vidya, the Zoom is all yours. Thank you very much.
Thank you. Let me start sharing my screen. Okay. Okay, I'm going to just minimize things and then I'll start. Okay, good. Okay, so actually it's a real pleasure to be giving a talk at the autumn meeting of the Physical Society of Brazil. And in fact, I was actually hoping to be here. Look at how gorgeous it looks from up above. I really hope that this is not the last time I'm invited to give a talk here, because I would really love to be there in person. However, I'm also happy to be giving this talk online, and I hope you get something out of it. Please feel free to interrupt me with questions if you have anything urgent. So today I'm going to be giving a talk about how you can realize and measure these particles called Myrana fermions. Really what I hope to do today is to describe the conditions under which these particles can be realized, and also give you one example of a particular system where we believe that we've actually seen such Myrana modes. For this work, the STM, which is scanning tunneling microscopy work, was done in my lab by Zhenyu Wang and George Olivares Rodriguez. We had theory support from Taylor Hughes and Dirk Moore, and we had beautiful single crystals from Genta Gu in Brookhaven National Lab. So the story of Myrana fermions actually starts back with Paul Dirac in 1928. Dirac was searching for the relativistic version of the Schrödinger equation, and finally came upon what we now call the Dirac Hamiltonian. And this Dirac Hamiltonian is actually really simple. It describes particles traveling close to the speed of light. And if such particles have no mass, then the Hamiltonian looks like this. It's basically proportional to the momentum. And you can solve this Hamiltonian quite easily and obtain the relationship between the energy and the momentum of these massless, now we call them Dirac particles. And we know from light that the energy momentum relationship is actually linear. Now, for particles like electrons traveling close to the speed of light, you can add a mass term and you can solve the Dirac equation. And now the energy momentum relationship looks like this. One of the interesting consequences of Dirac's equation, which puzzled him actually for a while, is the fact that you get both positive and negative energy solutions. And now we know that these negative energy solutions are actually antiparticles. And for the case of electrons, the antiparticles will be positrons. And when a particle meets an antiparticle, these two can combine and annihilate each other. Basically about 10 to 12 years after Dirac wrote down his Dirac equation, Myrana came up with another equation. Basically, the equation tells you that there can exist particles in nature, fermions rather, in nature, that are their own antiparticle. Just to go back to electrons for a second, the positron is a completely different particle compared to the electron. Its charge is different. Whereas Myrana postulated the existence of fermions, where the particle and the antiparticle are the same. So these kinds of particles can actually annihilate each other. And if you think about it for a second, if you want a particle to be its own antiparticle, you need the particle to be a neutral particle. And also, because these are fermions we're talking about, these are, in the simplest cases, spin half particles. So ever since Myrana postulated this, there's been a search amongst fundamental particles for these Myrana fermions. And in fact, as it turns out, all known fundamental particles are either Dirac fermions, and no Myrana fermions have yet been discovered in our universe. So the only outstanding possibility that we know of today is the neutrino. And so there have been many experiments that have been designed to figure out whether neutrinos are in fact Myrana fermions. And let me just show you how complicated these experiments can be. There is a way to actually figure out if neutrinos are Myrana fermions. And the way to do that is to look for this particular kind of decay called the neutrino-less double beta decay. So this is a decay of an atomic nucleus where you see two neutrons that go into two protons and two electrons. And if you can find such a decay, usually such a decay would actually give out also neutrinos. But if you can find such a decay path with no neutrinos, then it proves that neutrinos are in fact Myrana fermions. So here, for example, is what people call the Myrana demonstrator, and it's deep underground, and it's 40 kilograms of germanium and so on and so forth. And the purpose of this demonstrator is really to give you proof of concept, basically, that such a demonstrator might be able to prove or disprove this idea. And really the actual demonstrator, the actual experiment, will be a much bigger experiment on a much larger scale. So you can see that finding these Myrana particles in nature has been pretty complicated. However, in the last 2 decades, we've realized that we can actually see such Myrana fermions as quasi-particles in solids. So I love this example of a quasi-particle. So a quasi-particle in solid is just a dressed particle, meaning you take an electron and you add all its interactions with phonons or with other excitations in the system, and that dressed particle is what we call a quasi-particle. It's very much like a skier going down the slope, and as the skier goes down the slope, he's surrounded by this cloud of snow, and in fact, for some time, the skier and the snow are one entity. And that's what quasi-particles are. It's these dressed electrons. And as it turns out, we've been able to show that in solids, you can realize the same kinds of Myrana fermions, but as quasi-particle excitations. Just as an example, just to start you off through just thinking about it, if you take a nanowire, which has strong spin-orbit coupling, and you place it on top of a superconductor, and you turn on a horizontal magnetic field, then theory tells you that you should realize these bound states, Myrana bound states, at the ends of the nanowire. So the question is, why are we interested? There are actually fundamental reasons that Myrana fermions are interesting. One is these Myrana fermions are actually non-abelian particles. So unlike fermions or bosons, which acquire a +1 or a -1 when you exchange them, when you exchange two Myrana particles, you get a phase. And not only do you get a phase, but actually the end state can be different from the states that you started with. So these are actually now non-abelian particles. So if you can realize Myrana fermions in solid state matter, then you might be able to understand the properties of these Myrana fermions. They're also actually potentially useful as qubits in quantum computers. That is because, I'll show you in a second, each electron is actually composed of two Myrana fermions. So if you have an isolated Myrana fermion, its partner exists somewhere else. So in the example that I was talking about, that is the nanowire, you can have these two Myrana fermions spatially isolated on the ends of the nanowire. And because it takes two Myrana fermions to form a physical particle, which is an electron, these two Myrana fermions are not actually easily disturbed. So you can actually use these Myrana fermions for fault-tolerant quantum computation. So I'm going to try and answer this question first, which is, how do you create a Myrana fermion in a solid? Let's just start with the premise, the basic idea for Myrana fermion, which is that it is a particle that is its own antiparticle. So if you wanted to write that down mathematically, you would say that you want the creation operator and the annihilation operator for this particle should be identical. Now, if you think about which solid system might have such a property, you immediately think of a superconductor. In a superconductor, one of the fundamental properties of a superconductor is that it has particle-hole symmetry. So one might use a superconductor to actually realize these Myrana fermions. So I promise you this is the only slide with any equations at all, but let me just go through this. So let's just start with a superconductor. We know that the low energy excitations of a superconductor are Bogoliubov quasiparticles. What these really are, it's actually really simple. Each quasiparticle is made up of two pieces. One is an electron and the other is a hole. So these Bogoliubov quasiparticles, which are actually equal or maybe slightly unequal superpositions of electrons and holes, are ideal candidates to have a Myrana fermion because naturally they are neutral particles. So let's just take such a superconductor and look at the Bogoliubov quasiparticle excitations. And so here are the creation and annihilation operators. And now we want to construct this Myrana fermion. So we want the creation operator to be equal to the annihilation operator. And now if you want these two operators to be equal to each other, you realize that even if each of these excitations is composed of equal amounts of electrons and holes, you still have a problem. And the problem is that the spin can never be equal. So you can see here that this is a spin up, which is attached to this operator, whereas this is a spin down. So there's one more thing that you need. You need to use a superconductor, but you also need to somehow get rid of spin as a separate degree of freedom. And if you can achieve these things, then you can create Myrana fermions in a solid. So the real question is, how do we eliminate spin as a separate degree of freedom? And I want to show you three different ways of doing this. The first way is actually a very simple way. You can actually use what we call triplet superconductors. We're all familiar with singlet superconductors, where you have a pairing of electrons with opposite spins. However, we've known for a long time that you can also have superconductors where equal spin electrons are paired. And you can show that when you have such triplet superconductors, under certain circumstances, these are perfect platforms to realize Myrana fermions. And one really simple hand-waving way of understanding this is the fact that in a triplet superconductor, Spin is not important anymore because the pairs are made up of equal spin electrons. And so in some way you've gotten rid of spin as a separate degree of freedom. You don't have to worry about spin anymore. And in fact, the natural excitations of such a triplet superconductor are indeed Myrana modes. So, where do you find these triplet superconductors? Actually, many of these triplet superconductors belong to this class of materials called topological superconductors. And a topological superconductor is actually a distinct state of matter in the following sense. You may have heard of topological insulators. Topological insulators are materials where the topology of the bulk, and in fact, I'm going to talk about topological insulators in a bit, but just to give you an overview, the topology of the bulk of the material determines what happens on its boundaries. For example, a material can be topological for a quantum anomalous Hall system, is topological in a particular way such that it has only one boundary mode. In a very similar way, if you have a topological insulator, a superconductor, then you can have these boundary modes that are actually Majorana fermions. So this is one way of realizing Majorana fermions, which is to find such topological superconductors or these spin triplet superconductors. They're not synonymous, but some spin triplet superconductors may be topological. The problem is there aren't many triplet superconductors in nature, and in any case, the temperature at which they superconduct tends to be very low. So what else can we do? Here's another way of realizing Majorana fermions. And this is the example I was telling you about before. Here you use a semiconducting wire with strong spin orbit coupling, and you place it on top of an S-wave superconductor. And then you need a third ingredient. This third ingredient breaks time reversal symmetry. So something like ferromagnetism or turning on a magnetic field. So if you add all these ingredients together, then you could get Majorana fermions at the ends. So how does that work? Well, okay, let's just start with a semiconducting wire with strong spin orbit coupling. We know that when spin orbit coupling is strong, the bands are split in this fashion. These are the dotted lines I'm talking about, right? And the spin character of these bands looks like this. Now let's actually, now let's turn on magnetism, right? And when you do that, you can you create a gap right at this crossing point, and you get these solid bands. And now if you can put your Fermi energy inside this gap that you've created, then you're in a situation where there's only one band crossing the Fermi energy. You've completely gotten rid of this other band. And moreover, this band has a very well-defined spin. So if you can engineer the system to have band structure like this, and then you put this semiconductor on top of a superconductor, you open up a gap on just this one band, then you get Majorana fermions at the end. So you can see just from my description that this is very complicated to do. And in fact, because this is so complex, many of the experiments on such systems have been done with transport, and it's been really difficult to do STM experiments on these kinds of nanowires. The third possibility, which is actually the simplest in some sense, is to use this class of materials that I alluded to before, which is topological insulators. So just let me, allow me to go through a very short digression about topological insulators, and then I'll get back to Majorana fermions. So we've known now for, maybe 15 years that by thinking of materials through the eyes of topology, we can put significant constraints on what can or cannot happen. So just to start with, topology is the mathematics of shapes. So topologically speaking, these three shapes on the top are the same, and quite distinct from the shape below, which is a donut. So this is a very well-developed field of mathematics, and you can define something called an Euler characteristic for these shapes that are shown below here. And if you calculate this Euler characteristic actually is an integral of the curvature, the Gaussian and geodesic curvatures of these objects. So for example, if you were to calculate the Euler characteristic of a sphere, you would get an integer, which is 2. If you were to calculate it for a single donut, you get 0. And for a double donut, you get -2. Now, the question is, what is the significance of these Euler characteristics? And so here's the significance. If you were to take a sphere and just adiabatically deform it without punching a hole through it or anything, as long as you deform it adiabatically, this characteristic chi does not change. So this chi, in some sense, is an invariant of these shapes. So in fact, if you want to go from one of these shapes to the other, you have to do something quite dramatic, like punching a hole through the system. So very similarly, just like you have these, the topology of shapes, you can also have topology for band structure. So earlier at the beginning of the talk, I showed you the momentum, energy momentum dispersion relation for just a very simple system where you have just one band. In general, in a solid, these energy momentum dispersion relations can be quite complicated. For example, this might be an energy momentum dispersion for some kind of an insulator. But the interesting thing here is these bands in momentum space have, they form some kind of a topological manifold. And similar to solids, you can define a topological invariant for these bands. And you can show that some bands are topologically distinct from other bands. And as it turns out, these bands that are topologically different are called topological insulators. So let's say you have such a 3D material, which is a topological insulator. The interesting thing about such a material is that because of the topology of the interior, the boundaries of this material must have very special states which only live on the boundaries. So these are two-dimensional states which live on the boundaries. And these two-dimensional states have very unique properties. One of the properties of these two-dimensional states is that they have Dirac dispersion, which is that these electrons behave like massless relativistic fermions. The other interesting thing is that as long as the topology of the bulk is not changed, these states are never destroyed. So just to give you a sense of how different these states are, if you think of a normal two-dimensional electron gas, for example, take gold or silver, on certain facets of gold and silver, we know that you have this two-dimensional gas of electrons. If you look at their dispersion, these electrons behave like normal electrons in a band, and they have parabolic dispersion. And at any given energy or momentum, you would have two electrons, one spin-up electron and a spin-down electron. If you contrast that with the surface states of a topological insulator, you can see that it's completely different. First, the dispersion is linear, right? So this is Dirac dispersion. Second, at any given energy and momentum, you have only one species of electron. Here I've shown it as spin-up. So you've actually lost the second branch altogether. In fact, you might ask where it is. It's on the other surface, as it turns out. In any case, because of this kind of very special dispersion, these materials are ideal to be used to realize Myrana fermions. So, okay. So in this talk, what I'm going to show you is how you can use these topological insulators in proximity with a superconductor to get two kinds of Myrana modes. One kind of Myrana fermion is a bound state, meaning that it lives in the vicinity of a vortex in a superconductor. And the other kind of Myrana fermion is a propagating state, and it actually moves along the boundary between two superconductors. So in 2008, Charlie Kane and Liang Fu showed that if you take the topological insulator that I was showing you earlier, if you take this topological insulator, put it in proximity with a superconductor, and turn on a magnetic field, then in the vortex cores, you get Myrana bound states, right? That's one way of realizing Myrana bound states. And so remember what I told you about the essential ingredients you need to get Myrana bound states. You need a superconductor. You need some way of removing spin as a special degree of freedom, and you need some way of breaking time reversal symmetry. So this thing does everything. You have the superconductor. The topological insulator basically gets rid of spin as a separate degree of freedom. And the reason is that in a topological insulator, I didn't show you this, but like I was saying, there's only one species of spin for a given momentum. And in fact, spin is locked with momentum in a topological insulator. So essentially, once you know the momentum, you know the spin. So that takes care of that. So there are two ways in which you can get Myrana bound states. One is you turn on a magnetic field, and in the vortex cores, like I said before, you get Myrana bound states. And the other thing they showed was, if you can engineer the system such that you have two superconductors, and these two superconductors have a phase difference between them, then at the boundary between the two superconductors, what you will find is these propagating Myrana modes, meaning they can move as a function of right along this boundary in one dimension. Okay, so this is what we'd like to actually realize. And before I show you the experiment, let me just show you how you can use these Myrana fermions for quantum computation. So this is just one example. Let's say you have two vortices in your system. Or in fact, here what's being shown is 4 vortices. So each vortex, right, has one Myrana fermion. And then if you could exchange these vortices, perhaps by moving them with current, then you can end up in a state that's an entangled state. And such entangled states are what you need to do quantum computation. Okay. All right. So in 2015, there was a breakthrough. And the breakthrough is the following. This is what enabled us to study these modes with scanning tunneling microscopy. So this geometry that I've been describing, which is, you need a superconductor and a topological insulator, and so on, that's pretty complicated. And it's really hard to engineer and do scanning tunneling microscopy on it. But in 2015, they discovered that there is this particular material, which is iron selenium tellurium, which is actually an intrinsic proximatized superconductor. I'll tell you what that means in a second. So what this is we've known for a long time that this material is an S-wave superconductor. So in the bulk, it's a superconductor. But what they found in 2015 is that it's also topologically non-trivial. So that means that this material on the surface has these interesting surface states that I was telling you about. So in one material, you have both superconductivity as well as the presence of these two-dimensional Dirac fermions on the surfaces. So one imagines that if one could turn on a magnetic field and look at the vortices in this material, you should be able to actually find Myrana fermions. Okay, so before I show you the experiments, let me just give you just a little bit of background on the system. So this is the phase diagram. It's an alloy of selenium and tellurium. So one end of this phase diagram, which is the FeSe end, is actually a superconductor. The other end of the phase diagram, which is the FeTe end, is a spin density wave system, or think of it as an antiferromagnet. Now, when you create this alloy, as it turns out, somewhere in the middle right here is where the interesting Myrana physics happens. This is where the material becomes topologically non-trivial. Just for the experts, the band structure of this material looks like this. You have, this is the Fermi surface. You have, multiple pockets crossing the Fermi surface. And, there are these two pockets at the gamma point, and then there's the pocket at the M point. The reason to show you this is to tell you that each of these pockets that crosses the Fermi energy should actually give rise to its own superconducting gap. So when we measure the superconducting gap with STM, we might see 1, 2, 3 gaps coexisting at any given location. So in 2018, a few years after the material was predicted to be topologically non-trivial, they carried out angle resolved photoemission measurements where they could see this direct. So this is energy, this is momentum. So you can see there's this band that crosses the Fermi energy. It's got linear dispersion, and they could show that this band was actually a surface state. So this is sort of very promising. This seems like just this measurement gives you hope that this material might be able to host Myrana modes. Okay, so now let's come to scanning tunneling microscopy. So the rest of the talk is about STM. And scanning tunneling microscopy is actually a very simple but very powerful instrument. It consists of a very sharp metallic tip that you bring to within a few angstroms of the surface that you would like to study. So you shouldn't be touching, but you're very, very close. And you apply you apply a potential difference between the sample and the tip. And electrons then tunnel from the sample to the tip or vice versa. This is quantum mechanical tunneling across this vacuum barrier. Now, because these two things are so close to one another, you need to be very careful not to let noise into the system. So of course, all of this is done in the basement, and you have both acoustic, soundproof rooms, as well as vibration isolation with air springs. So the way the STM works, it's really simple to visualize. So here's your vacuum, right? So there are no states in vacuum. You can think of the tip and the sample as just a bucket of electrons filled up to the Fermi energy. When you bring them in proximity to one another, the two potentials equalize, right? The electrons go from one to the other and the Fermi energies become the same, just like two buckets of water. And then when you turn on some potential difference between the two, just by, just a bias voltage between the two, you raise the Fermi energy of one with respect to the other. And now electrons can tunnel from the filled states of the sample, in this case, to the empty states of the tip. And it is this tunnel current that we measure. And this is the only measurement we make. We measure the magnitude of this tunnel current as a function of position as the tip is rastered across the sample. We measure the magnitude of this tunnel current as a function of bias voltage. And we can even measure the magnitude of the tunnel current as a function of distance from the sample. But the only actual measurement we make in an STM is the magnitude of the tunnel current. And you can see even pictorially that this tunnel current must be proportional to the integrated density of states of both the sample and the tip. That means that by differentiating dI/dV, you should be able to measure the density of states of the sample. So what do we expect? For example, if you have a metal, then you expect a very flat density of states. So if you were to measure the density of states, dI/dV, you would simply measure a straight line going across the Fermi energy. For us, the Fermi energy is always 0 volts, so 0 bias. Whereas if you measure the density of states of a superconductor, a conventional S-wave superconductor, you would say no states near the Fermi energy up to the gap value of delta. And at the gap value, you would see these sharp coherence peaks that tell you what the magnitude of the gap is. So this is what a superconducting spectrum should look like, shown in red here. So in my lab, we have multiple scanning tunneling microscopes. The STM that we use to do these measurements I'll show you today was this Unisoku, which is the commercial scanning tunneling microscope from Unisoku in Japan. It can go down to 300 millikelvin, and it has a 11 Tesla field. So in order to do scanning tunneling microscopy measurements, you have to expose fresh, clean surfaces. And these surfaces cannot be exposed to air, because if you expose the surface to air, it absorbs all kinds of things, oxygen, nitrogen, and so on. So what we usually do is we cleave surfaces in vacuum. And if you look at the crystal structure of FeSe, which is basically the material that we're going to study, then it's got these layers, right? Each layer is composed of one layer of iron atoms, which is shown in purple, and a layer of tellurium atoms or selenium atoms on top, and another layer of selenium or tellurium atoms below. The interesting thing is that the layer of selenium or tellurium on top is shifted by half a unit cell from the layer below. Now, because STM is mainly sensitive to the surface, if you do STM on the surface of this crystal, for example, what you'll see is the selenium or tellurium atoms, which is going to form a square lattice shown here. Okay, so these are the ones in the layer below, right? And the purple ones are the iron atoms. We don't see any of that. So this is what topography would look like with a scanning tunneling microscope. Each dot is in fact an individual selenium or tellurium atom. And you can zoom in and you can see these are the seleniums and tellurium atoms on the surface. The reason that this topography is so inhomogeneous, meaning that you have bright regions and dark regions, is that this is a 50-50 alloy of selenium and tellurium. And as it turns out, the seleniums and the telluriums are not equally bright in STM topography. Okay, now let's measure the density of states. And I already showed you what you should expect. If you this is a superconductor, so you should have 0 density of states at the Fermi energy, and then you should see sharp coherence peaks. So if you measured spectra along this line, then that's what this is. This is actual data. So let's just focus on the first point. So here you can see the coherence peak, flat 0 density of states, and then coherence peaks on the other side. There are a couple of things to point out. One is you don't see just one coherence peak, you see 1, 2, 3. And the reason that you see multiple coherence peaks is exactly what I told you before. You have these multiple pockets crossing the Fermi energy. Each of them develops its own gap. And in fact, we can sort of get an idea of what these gaps should be from other measurements, like specific heat, RPES, so on and so forth. And if you look at all of this data, you realize that STM should be seeing really 3 low energy gaps at these different values. And one of these, which is 1.8 MeV, is the superconducting gap in the special surface state that I was talking about, which is, we think, the topological surface state. So we can go in and do a statistical analysis of all the gaps that we measure. This is the analysis. So from these histograms, we can get the mean values of 1.3, 1.8, and 2.4 millivolts. And the important thing is that these numbers match very well with previous measurements of the gaps. And the other important thing is we see this 1.8 millivolt gap, which is actually associated with this topological surface state. Okay, so now we have all the ingredients that we need to see Myrana fermions. All we need to do is turn on a magnetic field. And the question is, what should we see? So remember that in a superconductor, let me just go back here. In a superconductor, there is 0 density of states at the Fermi energy. So if I measure the density of states in this field of view and plotted it as a function of position, right? It should be 0 everywhere. So this whole field of view should be dark, black, because it's 0. So that's what you would see if I measured the density of states without a magnetic field. So that's what it should look like. And now let me turn on a magnetic field. Now I'm going to measure the density of states exactly at 0 bias, and that's what it looks like. So suddenly, in the presence of a magnetic field, you have all these bright dots. Each bright dot is a position where the magnetic flux has actually managed to penetrate through the sample. So inside each of these bright, this is called a vortex core. Inside this, you have sort of normal quasiparticles, which of course, this is a superconductor. So you have Bogoliubov quasiparticles that exist inside this vortex core. And outside, of course, it's still superconducting. And these vortices typically form a nice hexagonal lattice. That is what you're beginning to see that here. So this is a hexagonal lattice. Now, if you go to the, sorry about that, if you go to the center of one of these vortex cores, what you find is a sharp peak in the density of states right at zero bias. And theoretically, that's exactly what you expect for a Myrana bound state. So in fact, this experiment was done not by us first. This data is ours, but then this experiment was done in 2018, where they measured the same material and found that only 30% of these vortices that I showed you earlier, only 30% of them show these beautiful zero bias peaks. And the others show peaks at different voltages. So the real question is, how do you know that these are Myrana bound states, right? What is the proof? In fact, as it turns out, think about what a vortex core is. It's a sort of a normal region full of quasiparticle excitations inside a superconductor. So these quasiparticles are actually confined inside the vortex core. So in fact, they occupy particle in a box states, and these states are called Caroly-de Gennes metricon states. So if you go to the vortex core of any superconductor, you should see a series of states discrete levels filling up the vortex core. You can show that the energy of these vortex core states it's proportional to the square of the gap magnitude, which is the distance between the coherence peaks, and it's inversely proportional to the Fermi energy. For our system, these ordinary vortex core states, you can ask where should they live? So in this particular system, if you put down all the values for the gap, the Fermi energy, so on, you can show that these ordinary vortex core states should be, the first one should be 100 millivolts from the microvolts, sorry, 100 microvolts from the Fermi energy. So, this is work by Hanaguri in Japan, and they've shown that these zero bias states are in fact at zero to very high precision and very far from these 100 microvolts that the ordinary Caroly-de Gennes state should be. There are also other measurements that I don't want to get into, this is showing you that the spacing between these special vortex core states is actually integer instead of half integer. So if you take all of these, the supporting evidence, then there's a lot of compelling evidence to indicate that these zero bias peaks that you see in these vortex cores are indeed what we've been searching for all along, which is Myrana fermions. Okay, so in the last 5 to 10 minutes, I think, I'll just talk about another way of realizing Myrana modes, which is to look at the boundary between two phase-shifted superconductors. And here now, remember, these are not bound states, these are propagating states, so they're going to look quite different. So the theory prediction is that if you have two regions of superconductors with a phase shift between them, in fact, if the phase shift is pi, then you will see helical Myrana modes living here right at the boundary. But if you have any random phase shift, you will also have Myrana modes, except they'll be gapped, that's all. So this is what theory says, and let's see what we get in experiment. So what do we have? To realize these propagating states, you need superconductivity. You need the material to be topologically non-trivial. So I've shown you that we have both in this iron selenium tellurium. And finally, you need a region where on one side you have one phase in your superconductor, and the other side you have a different phase. And ideally you want to have a pi phase shift. So astonishingly, as it turns out, this material gives you that, just like that. So this is calculation done by Jiangping Hu in 2013, where they show that if you take into account, the crystal structure, the nearest neighbor hoppings, next nearest neighbor hoppings, and so on, then the superconducting phase is actually, this is a side view of the crystal. So these are the tellurium atoms on top, these are iron atoms, and these are tellurium atoms below. So this is one layer. This pluses and minuses refer to the phase of the superconducting order parameter. So that's what it looks like in real space. So if you could engineer the material where there's actually a physical flipping of the top and the bottom layer, then you would get indeed a pi phase shift right across this boundary. So that's what we're looking for. So a lot of the region of the sample looks really beautiful and pristine with no domain walls. But sometimes you can find regions with domain walls. And not all domain walls give you this pi phase shift. But you can go searching and you can find a domain wall where the crystal structure has kind of flipped, right? It's like a stacking fault. So if you look at this kind of a region and you take a Fourier transform, what you find is that these peaks are, there's only one peak, but if you zoom in here, you find that there's a splitting of the Fourier transform peaks. And what that basically tells you is that the atoms on one side and the atoms on the other side are phase shifted with respect to each other. And you can sort of use your eye to track the atoms on one side and track them on the other side. In any case, whatever method you choose, you can show that the atoms on the two sides are actually phase shifted with respect to one another. So this is sort of the ideal condition to get this pi phase shift in the superconducting order parameter. So now you can measure the DIDV spectrum far away from this domain wall, and it's this blue spectrum here. And if you go right to the domain wall, this is what you see. So you don't see a huge peak that we saw before in the vortex core. Instead, you see this flat density of state. This is finite density of states, meaning you have inside the superconducting gap, you have a whole bunch of states that are filling up the superconducting gap. The superconducting gap still exists. You can see it go down, but there's an extra density of states filling up the entire superconducting gap from one end to the other end, okay? So in fact, you can see this. So you can take spectra along this line in pink. And if you do that, this is just a color plot. You can see that this is the superconducting gap here. It's spectra along this line. It's dark. And as soon as you get to this line, you have this finite density of states inside the superconducting gap. More interestingly, this is like the density of states is a constant, right? So you have a finite constant density of states. So the question is, can this be a signature of Myrana fermions? And so the question is, what do you get if there's this pi phase shift? And the answer is that we know already from Fu and Kane's calculation that what you should see are these linearly dispersing states in one dimension. And if you ask the question, what is the density of states of anything that's dispersing linearly, it's flat, okay? So anything with linear dispersion in one dimension has a constant density of states. And that's exactly what we see. So all of these states are these propagating Myrana fermions that live along these domain walls. So is there any other proof that these might be Myrana fermions? This is the last thing I want to show you. And the answer is yes. Because these Myrana fermions are topological, they have certain topological properties. One of them is that if as you change energy, the spatial extent of these Myrana modes should get larger and larger until when you reach the edge of the gap, it should basically span the entire area. So this is your domain wall. And this is what the Myrana fermions look like at zero bias, meaning right at the Fermi energy, they're very well confined to the domain wall. And as you get away from zero, so this is increasing energy, as you increase energy, you can see that in real space, the spatial extent of these Myrana fermions is getting larger and larger until you reach 1 millivolt, which is very close to the edge of the gap, where it spans the entire sample. Okay, so this is it. So I hope I've shown you how you get Myrana fermions. I hope I've told you why they're interesting. There are many different ways to get Myrana fermions. You can have a topological superconductor. You can do something quite clever by using nanowires with spin-orbit coupling, put them on a superconductor and so on. And you can also, if you're lucky, find these kinds of materials where you have superconductivity and topology all in one material. And if you do find such a material, then you can go looking for Myrana fermions, either in the vortex cores or in sort of phase-shifted regions. And you know, there's a lot of indication that FeSETE might be one such material. And certainly all the experiments that have been done so far seem to support that. I think there's a lot more to be done. You know, this is far from settled. The smoking gun experiment of Myrana modes would be to actually braid them and to see evidence for that these are non-abelian particles. And so a lot remains to be done. Thank you for your attention.
Thank you, Professor Vidya. Very nice talks. We are open for questions. Please open your microphone. Yes, Luis Gregorio, you can open your microphone. Hi.
Hi, Chris. Very nice talk, Vidya. Really enjoyed it. And actually, I have two questions regarding the vortices on this iron selenide telluride.
Yep.
I read the paper from the Japanese group that you mentioned.
Yep.
And if I remember right, they tried to find correlations between the position of the vortices and the topography, the concentration of selenium and everything. And it was really hard to find any correlations there.
Correct.
And so my question is, since you have this statistics of the gaps and you know the gap of the surface state, can you do, say, try to find correlations between the vortices where you see the zero bias peak and, you know, the gap?
Yeah, I had suggested this to Hanaguri because he was working on this, and I'm going to ask him again because this is a really interesting question and it's worth doing. He has a lot of data already, and so it's not worth taking the data again. I think it's a really good thing to do. So we could just take his data and analyze it ourselves. But it's really worth looking at whether there are correlations between the gap magnitudes of the different gaps and the existence of this Myrana bound state. One thing I have to say though is in Hanaguri's measurements, 80% of the vortices actually showed these Myrana bound states at low fields, which is a large number. So very few of them didn't show, and also one has to remember that sometimes these vortices are pinned to impurities. So then it's a completely different story. So if you toss all those out, I think that they had a pretty high success rate at low fields of seeing these Myrana bound states, if that's what they are, or seeing the zero bias states, yes.
And the second question is with regards of manipulating those vortices to try to do some braiding. So can you do some sort of manipulation with the STM tip to rub them around?
Let me just show you. Actually, you can, because in fact, you can
Very
see.
nice question, Luisa. I would like to ask that too.
So you can, let me show you this. What are you seeing? Are you seeing just my screen or are you seeing yourselves as well?
I'm seeing your screen.
The PowerPoint
okay, good.
on your screen.
Okay, so you can, because I just want to show you this. It's quite amazing. We see this all the time. See this vortex here? See these lines? You know, this line, it's not noise, it's the vortex moving. So even the STM current, which is nanoamps, which is tiny, is able to move such a vortex core. So if you can imagine, you can move it in all kinds of ways. You can either have current flowing, like you can have channels of superconductors and have current flowing, and they will move. They move very easily. Or you can have, you know, especially if they're sparsely spaced, like very spaced far apart. Or you can even have a sort of a magnetic tip and have a large tunnel current and simply drag them along with you. Yeah, these experiments have not been done, but it would be really nice to do, to actually show that you can move these things in a controllable fashion. But they're I mean, the very fact that, and every vortex lattice I've ever seen always has vortices which want to move. They really do want to move.
All right. Well, thank you. Very nice talk.
Thanks.
Professor Vidya, do you think that, is there any other technique like measurement from which we can have evidence, not proofs like those from STM, that we can just have like some feeling if the sample has some, or can have, or something related with the Myrana zero modes, or?
They do transport, and they look for, you know, transport has been done on many different geometries. Just, you know, the nanowire geometry I was telling you about, the first experiments were done with transport. They also do spectroscopy, DIDV is what they're doing. But they do that in transport, and they can see similar signatures in transport as well.
Okay.
So, but other than that, let me think for 1 second. You know, it's really hard. I guess there are people thinking about microwave measurements that could, you know, perhaps give you some signatures of, if you can entangle them, maybe you can see signatures that they're entangled, but it's very tricky. It's very tricky.
I have another question, if I may.
Sure.
Regarding the phase diagram of iron telluride iron selenide, what happened with other samples that are not the half-half tellurium selenide, that they don't show those domains?
You know, so the real question you can ask is, I guess, over what range is this material, if all of this physics is correct, right? Let me just preface what I'm about to say with that. If this physics is correct, then you can ask the question, over what range is this material topologically non-trivial? And I think, as far as I know, there's a pretty large range around 50-50. So, so, you know, I've drawn this box in a very vague, I didn't mean to be precise here. So I think it extends quite a bit on either side. This FESE is not topologically non-trivial. So its phenomenology is completely different. In fact, we've looked at domain balls in FESE and it looks completely different. And so, yeah, so we know this end of the phase diagram doesn't show this phenomenology at all.
Okay, great, thank you. Now we have a question from Poliana. Poliana, please open your microphone.
Okay, thank you. Hi, Vidya.
Hello.
Thanks for the very nice talk.
Sure.
So you showed two experiments. One related to the Majorana bound states, and the other you were showing the helical Myrana states.
Mm-hmm.
If I understand it correctly, both states are different with respect to the statistics.
Mm-hmm.
So, and I know of at least one paper that talks about braiding the helical Myranas or the chiral Myranas.
Mm-hmm.
Do you have something, do you have any comments on that? Or do you think it's possible to do that?
Yeah, so I think one problem we have in this particular system, like you just said the words, actually, you said helical, and the braiding paper is about chiral Myrana fermions, right?
Yeah.
So to realize chiral, the way we know right now to realize chiral Myrana fermions is to start with a quantum anomalous Hall system and make that superconducting. And then because you start with just one channel, you end up with chiral Myrana modes. So this one, though, you have two branches. I don't know whether there are any schemes to braid helical Myrana fermions. That's the problem. I think that it's hard enough to think about braiding. There are two problems, right? One is manipulation and the other is readout. So how do you read, even if you do manage to exchange particles or braid these chiral modes, how do you read what happens after you've done the process? This is really tricky. So I think there's some ways to go before we can do that.
Okay.
Oh, good.
Okay, thank you.
Rodrigo, do we have questions on YouTube?
We have a question on the chat from Fabrizio.
Hi, Professor Vidya. Thank you for this great talk. My question is, at the end of the presentation, you showed us the last way to find Majorana Fermions, which are propagated Majorana Fermions. So my question is, how can you create this phase shift? Is it by using different magnetic fields or by using different types of superconductors? Can you explain that?
It's so if you want to controllably create a phase shift, the way we know is to by passing current. That's how we know to controllably create a phase shift. In my case, in this particular case, this was not done in a controlled fashion. We took advantage of something that occurs naturally in this material. So let me show you what that is. So if you look, that's why I showed you the crystal structure right at the beginning. So here's FeSETe, right? So these are the top selenium or tellurium atoms. These are the bottom ones. And these are shifted from each other by half a unit cell. So this is the top view. This captures this top layer, the middle layer, and this bottom layer, right? Everything is captured here. Now, so look at this. So I also showed you that paper, which suggests that the superconducting phase has this property where the top and the bottom layer have a pi phase shift between them. So if this is plus, this is minus, okay? So then because of the way the crystal is, you can easily imagine that when the crystal is made, it chooses, these atoms, these ion atoms have to choose whether or not they're going to have the selenium on top or not. So when the crystal is made, it makes a choice. Therefore, you can have different domains of the crystal, where in some regions you have these atoms on the top being selenium, and in other regions, the equivalent of these ion atoms would not have these seleniums on the top. So this is that domain wall. So on the left side of the domain wall, you can see these are the top selenium atoms, these in blue, right? And as you go across the domain wall, you can see that there's a shift in the crystal structure, where now you don't have the top selenium anymore. You have it phase shifted by half a unit cell. So if you can, because the crystal structure allows you to do that, you naturally find such domain walls in your sample. And because there's this funny, strange phase relationship between the top and the bottom, across this particular kind of domain wall, we expect the superconducting order parameter to have a pi phase shift. So it's a serendipitous discovery. It's not something we engineered.
Okay, thank you.
I don't see more questions.
I have one quick question.
Sure.
Yes.
At the beginning, you mentioned it's hard to do STM on wires. What's the difficulty?
It's not hard to do STM on wires. The problem is that it's getting these things to be clean is very hard. So STM is a very sensitive probe. If you have one single impurity in a sea of atoms, you'll be able to see that impurity. So if you have a nanotube that you've laid flat on the surface, you have to find a way to clean the surface and clean the nanotube, remove all the oxygen and the water and everything that's sitting on top of the surface. That's why we prepare our surfaces in vacuum, so nothing ever falls on the surface, right? So if you look at the topography here, there's nothing on the top, like not a single impurity atom that's sitting on top. Whereas if you prepare these nanotubes outside in air, it's going to be really dirty. So how do you clean it? That's one of the biggest problems. So, and then the second problem is, I guess how do you find them? Maybe you put a whole bunch down on the surface somehow, and then you go looking for them, right? And the third problem is, like I was telling you, it does require a little bit of fine tuning where you have to use a gate to put the Fermi energy inside this gap. That's why it's so tricky. So, you gotta use a gate to put the Fermi energy right. So, you have this semiconductor, you have the superconductor, and then you gotta take your gate voltage and put the Fermi energy right here. All these things are really difficult to do and do STM.
I see. Yes.
So that's the big problem, yeah.
I think Luis has another question. Please go ahead.
Hi, no, just a quick question regarding this problem of placing the Fermi energy.
Mm-hmm.
Now, of course you have those experiments from Alias Dani's group where they have these magnetic chains on, yep, say, superconducting surface with strong spin orbit.
Yep.
Now, is there a way to tune the Fermi energy in those systems, or you just
they're in a very good situation there, because I think because these are magnetic atoms, mm-hmm, they don't need this fine tuning of the Fermi energy, because the Fermi energy lives inside the superconducting gap. The superconducting gap straddles the Fermi energy, and so I think their mechanism is slightly different from this semiconducting wire, blah, 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 Rashba. I think, so there they do have these Myrana bound states, which show up at the ends. And in fact, when I first saw his experiments, my instant thought was, wouldn't it be lovely if you could actually make these wires by atomic manipulation? And I think that has also been done. There are groups in Germany that have made these wires by atomic manipulation. And then they've studied systematically how these zero bias modes develop as a function of wire length. So by picking up each atom and moving it one by one, you can make such structures. Yeah, it's pretty cool.
Yeah, Thank you.
Okay, so more questions to Professor Vidya? So I would like to thank you again for the excellent talk, and hope we can see more of that very, very interesting work coming from your group. Thank you very much, Professor Vidya.
Thank you so much for inviting me. It's been a real pleasure. Bye.
Okay, bye. So I would like to thank everybody for being here, and I would like to wish everybody to take care and be safe, and see you on the next of the meeting.